Okay, so let's help get you started. This is Unified Paper 2022, half-term homework task, progress point 3 preparation. Let's have a look at number 1, just to get started. Question number 1, table shows some data on the planet Venus. We've got a mass in kilograms, a radius in kilometers, so I'm just going to make a note times 10 to the 3 potentially there for a future calculation maybe. Density of the atmosphere, checking the units, kilograms per cubic meter. Period of rotation about the axis in hours, so just in case I make a note there, times 60 times 60, just to get it into seconds if I need to. Calculate the magnitude of the gravitational field strength at the surface of Venus. Give your answer to 3 sig figs. It's nice that they said give your answer to 3 sig figs, but let's say we weren't given that prompt and we were using the information presented to us in the form of the numbers to work that out. So I'll be using this equation here from the gravitational field section of the equation book. Little g equals minus big G big M over r squared. The definition of gravitational field strength is the force experienced per unit mass, and because it's to do with forces, I am expecting r to be squared at the bottom there. Before I do the calculation, I'm expecting it, because it's Venus, to be not too dissimilar to Earth, maybe a little bit less than Earth's. So minus from the equation book as well, 6.67 times 10 to the minus 11 times by the mass of Venus, which is straight off of the table, 4.87 times 10 to the 27, and divided by the radius of Venus, and this is where that times 10 to the minus 3 comes into play. So 50 times 10 to the 3 all squared, and that on the calculator is 6.67 times 10 to the minus 11 times by 4.87 times 10 to the, I've written 27 there and it's 24. 10 to the 24 equals, divided by bracket 60, 50 times 10 to the 3, close bracket squared, and like Earth, it's just a little bit smaller, so 8.8745. And then if I was not given that prompt, give your answer to 3 sig figs, I'd be able to work that out anyway, because that number is to 3 sig figs, that number is to 3 sig figs. This number here at the bottom is currently in its ambiguous state, so it could be 3 or 4. It's hard to tell whether that 0 is a significant figure or not. But because the other numbers are 3, the smallest number of sig figs is 3, therefore I'll write my answer to 3 sig figs with or without that prompt, 8.87. For part B, 2 identical probes, A and B, land on the flat surface of Venus. Probe A lands on the North Pole, probe B lands on the equator. Each probe has a mass of 760 kilograms and a volume of 1.7 meters cubed, so they're exactly the same probe. Part 1, calculate the centripetal acceleration of probe B at the equator due to the rotation of Venus about its axis. So for that, I'll be using the circular motion portion of the equation book, and the defining equation for circular motion, or the acceleration for circular motion, centripetal acceleration, is acceleration equals v squared over r, and I'll likely be substituting in v equals once all the way around the circle divided by how long it takes to go once all the way around the circle. So that's going to look like this. A equals v squared over r, and v equals once all the way around the circumference of the circle divided by how long it takes to go once all the way around. Combining those two equations will give me A equals 2 squared is 4, pi squared is pi squared. Here I've got r, which will be squared, divided by r, which will leave behind just r, divided by t squared. 4 times pi squared times. So r from the table above was 6050 times 10 to the 3. 6050 times 10 to the 3, all divided by time period, and this is where that hours into minutes into seconds thing becomes handy. So that's 5830. 5830 times by 60 times by 60 to get it into seconds, all squared. Typing that into the calculator. 4 times shift pi, squared, times by 6050 times 10 to the 3 equals, divided by, open brackets, 5830 times 60 times 60, all squared, equals, I typed it in wrong, let's try again, 4 times shift pi squared times 6050 times 10 to the 3 equals, all divided by 5830 times 60 squared, all squared, equals, and there we go, 5.4222 times 10 to the minus 7 meters seconds to the minus 2. And then this number here is 3 or 4 sig figs. This number here could be 3 or 4 sig figs. So I'm going to err on the side of safety and go with 3. 5.42 times 10 to the minus 7. If you wanted to throw in that 60 is to 2 sig figs, and write that as 5.4 times 10 to the minus 7, I'd be cool with that. Okay, turning over to the next page now for the next part. Okay, the atmosphere exerts the same upthrust on each probe. That makes sense because each probe has got the same volume. Using your answer to part A, okay, make a note of my answer to part A then. Part A was 8.87 newtons per kilogram. Calculate the upthrust acting on each probe. Okay, so upthrust is equal to, now traditionally it's things submerged in water, Archimedes and all that, but it's any fluid, so it's weight of fluid displaced. That could be water, it could be liquid mercury, could be a gas, the weight of fluid displaced. So it's going to be mg, the weight of the fluid displaced. Let's substitute out mass with density times volume, G. And then let's go back to the table and work out what the density of the atmosphere is at the surface. Density of the atmosphere is 65. Times what is the volume of probes? No funny business with the units, 1.7. 1.7 times by gravitational field strength we calculated in a previous question, 8.87, equals 65 times 1.7 times 8.87 equals 980.135. Now this one's very clearly 2 sig figs, 2 sig figs, so I'm definitely writing this one to 2 sig figs. Right, 80. Like so. Okay, nice little explain question. Good, that means it's more difficult. So it definitely says explain, it doesn't say state or describe. Explain which probe will experience the greater normal contact force from the surface of Venus. Okay, well let me try and use my drawing skills to explain what's going on here. Let's draw a nice biggish circle. Put like a rod there, an equator mark, and then the impression that we've got some sort of rotation going on. Probe A is at the top and probe is at the North Pole, and probe B is on the equator. Now, each of them are going to experience the same weight acting towards the center of Venus. And then for probe A, because it's not going in circular motion, it's going to have all of its forces add up to 0. And now I'm just deeply suspicious that we've been asked to calculate up thrust in the previous question. So I'll put a little up thrust on both of them, and that's going to be the same for both. So up thrust the same. But for A, I need the sum of all of these forces to add up to 0. So that means I need up thrust plus reaction force for A to equal the weight of A. But for B, I need the reaction force to be smaller. So I'll draw a smaller arrow, reaction force B, because I need, when I do the vector sum of all of these forces, for there to be a resultant force that's acting towards the center of the circular path that B is on, that A is not. So how can I start writing this as an answer? Because it's an explain answer, I need to write the word because plenty. The first statement, though, will have to be which one is going to experience the greater contact force, and that is going to be A. So let's state that. A will experience the greater contact force I think that statement will secure us one of these 3 marks, but I'm not going to leave it there, so we'll have to put a because. I'll change that to a comma, because. So I reckon we need one statement about A and one statement about B, so let's keep this sentence going for A, because it is not in a circular path or circular motion, not in circular motion, because it's not in circular motion, its resultant force is 0. Let's write that as a sort of mathematical expression. This is like 0 equals. Now I'm going to keep my strict rules of up as positive, down as negative. So I see this as 0 equals, and then I have to add up everything. So up is RA plus up thrust, and weight is acting downwards, minus mg. Therefore RA would be equal to mg minus u. Okay. Just to create some contrast, I'll change over to red pen for probe B, which I'll start writing about now. Probe B has the resultant force isn't 0 for probe B, so it has a resultant force that provides the centripetal force. So that means when I do the same maths here, it won't start with 0, it will start with mv squared over r, which is our centripetal force equation. In the diagram, I'm going to strictly go left is negative, right is positive. So that'll be minus, and that will be equal to reaction force B is to the right, so that's positive. Up thrust is to the right, that's positive. Weight is to the left, so that's negative. And then when I rearrange that to make that RB the subject, it will be equal to mg minus u and minus mv squared over r. Don't know why I hesitated there. But now when you do the like-for-like comparison of RA versus RB, they're identical there. And the reason why RB is smaller is because you need to leave a little bit left over for it to have a centripetal force, whereas RA doesn't require the centripetal force. Okay, so together I reckon there we've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of 70. And that means so far we've got 17% in this paper. You're welcome to record that on SmartLearn and come back to this for question 2 later if you want to. Presuming I've hit all the nodal points for the marking there, I'll double check the mark scheme later. Okay, it's over to you. Question 2 comes next.